So now we need to isolate each unknown variable in each equation respectively. So in other words, in the first equation, as you notice guys, I isolated the unknown variable x1, right? And how how have I done it? So the way to do so is I just move move anything else to the right hand side of the equality besides the unknown variable x1 for the first equation. So moving to the right x2, x3, and then dividing both sides by 5, which is the coefficient of the first unknown variable x1. I isolated x1, and now x1 is equal to 1 over 5, and in square brackets times 12 minus x2 minus x3. And I do the same thing for the second and third equations. So since we have 3 equations, I did the same thing for each unknown variable respectively. So for the second equation, I isolated the second unknown variable x2, and for the third equation, I isolated the third unknown variable x3, and I just rewrite each equation with respect to this rule. But there is one more thing before I start the iteration process. Well, I'm almost done prior to the start of the algorithm. In other words, before starting to the computation. The thing is that we don't know how many iterations this would take on. So one thing left here is that the very first values on the right hand side actually are the previous values, whereas the value on the left hand side actually would be the new value that we will be obtaining. So here don't forget to put to the power of each unknown variable the number of iteration, okay, just to represent the number of iteration. For instance, in the first equation, as you notice, I write k, which represents nothing but the kth iteration. And for the x1 on the left hand side, what I write here, just let me first erase this to clearly show you that, okay. And and I do the same thing for the others as well, okay, just erase it. All right, and here's what I put here is the k plus 1. Why is that? Because on the right hand side we use the older values, whereas on the left hand side we obtain the new values at the next iteration. So the same thing holds for other unknown variables as well. On the left hand side we obtain the new values, whereas on the right hand side we use the older values to iterate through the unknown variables. Alright, and the same thing holds for the third unknown variable as well, right? This is the power I put here above the unknown variables is nothing but the number of iteration actually, right? So in this way I know which iteration is that, right? Say k. Okay, well, now so it is time to start this iteration process, and the second step to take is what? So this is the first step, right? Remember, we have 5 steps actually to follow. The first step is to write each equation with respect to the unknown variables. So in each equation I isolate one unknown variables and move the other to the right hand side and pave the way for the start of the iterations actually. Alright, and the second step is choose an initial guess. And since we are not given an initial guess, then what are we going to do? We take our initial guess including all zeros. So we have 3 unknown variables here. So we have x1, x2 and x3. So our initial guess is for x1 is equal to 0 and x2 equal to 0 and x3 is equal to 0. This is our initial guess. Actually, this is the point where we start. And this is also actually a candidate solution, right? So because this is just the start. You see here this 0 to the power of x represents the number of iteration, and 0 means the beginning, the very first, before the first iteration actually, the beginning value. Okay, and when we take the value k is equal to 0, what it means? Okay, now let's start the iteration. After taking the first guess, in other words choosing an initial guess, then we start our computation. We are ready to start our computation process. And how do we start? Well, with the very first iteration. And the first iteration, right? So first iteration. Now let's apply our technique. If we take the value k is equal to 0, then starting from the first equation at the top, we have x1, 1. And this is the number of unknown variable, and this is the number of iterations. So in the first iteration, the value of the first unknown variable is, how will we compute it? It is 1 over 5 times the current values of x2 and x3, right? 12 minus the beginning value of x2 and x3, which we choose as 0, right? Our initial guess includes all zeros. So we take these values 0, and for x3 again 0. So we have 12 over 5, right? We got 12 over 5, which is equal to 2.4, right? Which is equal to 2.4. And how about x2? So actually what I found right now is the new value of x1. In other words, in the first iteration I find a new value for the unknown x1, and in the next iteration, if I repeat this process, I will use this newly obtained value for the unknown variable x1. Well, we will check whether or not we will repeat this process or we will continue or not, depending on the error tolerance. But for the time being, just try to compute the values. And for the second unknown variable x2, in the first iteration, we need to find its value, and it is 1 over 6 times 17 minus what? The first initial guess of x1 and initial guess of x3, and these are all zeros, right? Because we take our initial guess as all zeros. So we have 17 over 6, and if I also compute the decimal points, well, it depends on us. So we can write the first 2 digits, 5 digits, 7 digits in the decimal part. It is actually our choice, but if we want to write it down clearly, we can do it, right? So say this is the value of x2 in the first iteration. So this is the new value of the second unknown variable. And how about x3? Yeah, I apply the same formula, and the new value of the third unknown variable x3 is found by this formula again, 1 over 7, 20 minus initial guess of x1 and x2, which are both zeros. So 20 over 7, if we compute it, if we use our calculator, of course, we got 2.857143. So this is the new value that we obtained for the third unknown variable. Alright guys, now we are at the end of the first iteration. And how do we understand that we are done with the first iteration? Well, it is simple. We just put the values of initial guess for each unknown variable and find the new values of each unknown variable. So when we found all of the new values for the unknown variables, then we are done with the first iteration. And the thing to check out is, now we have updated the variables in parallel, so we're done with the third step for the time being. Of course, we will decide whether or not we should continue. And now we're in the fourth step. Now, do we need to continue these iterations, or we are done? In other words, is the termination criteria met or not? So how do we understand that? We look at the error tolerance, right? And what is the error tolerance? Now let's see how we can find the error tolerance. And error tolerance is what? So we look at the obtained results of two successive iterations. And since we are just done with the first iteration, we just compare what we have found now with those of initial guess. In other words, if you want to compute the error tolerance for each unknown variable, for instance, for the first unknown variable, what is our error rate? So error rate for the first unknown variable is absolute value of 0, because it is the first value of the first unknown variable, and our computed value at the end of the first iteration. So don't forget to take the absolute value. So we got 2.4. And for the second variable, our error again, right? We compute our error. So 0 minus, because the initial value of x2 was 0, but now the newly found value of x2 is this value. So taking the absolute value, we got 2.83, 3, 3, and 3. So this is for the second unknown variable. This is the error rate, error for the first and second. And for the third one, we do the same thing again. We just take the difference between the values of two successive iterations for the corresponding unknown variable, and this is 2.85, 71, 43, and this is 2.85, 71, 43. And these are the error rates that we obtained with respect to each unknown variable based upon the actually results of the two successive iterations. So the difference, we take the absolute value of the differences between the older value and the newer value with respect to the two successive iterations results. And now what are we gonna do? These are the error rates for each of them, and we take the max, right? We take the max of this. So here's the thing. In other words, we take the maximum of these errors and see whether or not all of them are less than the error tolerance. Okay, so we got 2.4, we got, just rounded up, 2.83. I avoid from writing all of the decimal part and say in short 2.85. And what is the largest of these three numbers? So 2.85, right? So this is the maximum error rate when we take into account all the newly obtained values for each unknown variable. And what is our error tolerance, right? Well, as a termination criteria, we need to select a value, right? We need to select a value that is associated with the error tolerance and say that our error tolerance, let it be 0.01, so 1 over 100. Say this is our error tolerance, and we check whether or not this is true. Okay, and if the maximum of these errors for the unknown variables is less than this error tolerance, then that means all the newer values are below the desired error tolerance, and that means we are done with our computation process, and then we stop and produce the output that we obtained at that iteration, and we don't keep iterating. But in our case, as you notice, in the second iteration we are not below the error tolerance, our predefined or pre-assumed error tolerance. And in this case, I assumed that we apply 1 over 100 error tolerance, right? 0.01. So this is my error tolerance. And what am I going to do now? Since we have not obtained the desired error tolerance, we repeat this computational process until we really reach to the desired error tolerance, right? Until all of the newly found values satisfy this error tolerance. So that means we keep going. We are just going on with the second iteration. And then what am I going to do in the second iteration? All right. Now up to this point, what am I doing? Again, let's recap, because it's a complicated process. Since we try to converge to an exact solution by taking an initial guess, we rewrite each unknown variable in each equation in the order from top to bottom, and then we take our initial guess as zeros for each unknown variables and put these values to produce the results of the first iteration. And now we found the new values for each unknown variable, and then we check to see whether or not we satisfy the error tolerance condition. Well, in this case, again, for this example, I preferred to select the error rate 0.01, so 1 over 100, and I find the errors for each of the unknown variables by taking the difference between two successive iterations. In the beginning, all the values were selected as zeros, but now we have these newly obtained values, and I just take the difference and take the absolute value and see what I got for what is the rate for each of the unknown variables, and then I take the maximum of these errors, and I got 2.85 for the first iteration. So this is the maximum error for the unknown variables, and I see that it is not less than the error tolerance I pre-assumed. So with what this means is I need to repeat this computational process because I have not satisfied the desired error tolerance yet. Alright? And now, in the second iteration, what should I do? Well, the formula is the same, right? I will keep applying the same formula, but this time, in the beginning, we take k is equal to 0 because I took the initial guess and I found the values of the unknown variables in the first iteration. But now we know the values of the first iteration, so we know the outputs of the first iteration. Now I plug these values to find the new values of the unknown variables in the second iteration. So now what I have is, for the x1, let's make it a little bit smaller. Okay, for the x1, now this is the value of unknown variable x1 in the second iteration. And what is that? What I need to do is I will compute by using the same formula which I just have rewritten before. Okay, and 12 minus, but just be careful about one thing at this point. At this time, I will use the most up-to-date values. So the values that I found at the end of the first iteration, I will not use the values that I take initially. Alright, so this time I get what? For x2 I get 2.83. I just keep it short, you can write it longer. And for x3 I get 2.85. Alright, so in other words, I'll be doing this in all iterations. So if I continue, for instance, suppose I find the values of the second iteration and I proceed to the third iteration, and then in the third iteration, this time I will use the outputs for each unknown variables that I found in the previous iteration, in other words in the second iteration, and it keeps going on this way until the termination criteria is held. So what I get is here 1.261905, and I do the same thing for x2 and x3 as well. So but this time again, be aware of one thing only, right? And what is that? So make sure that you take the correct value. So you will need to use the new values for the unknown variables that we found at the end of the first iteration. So this time the value of new value of the unknown variable x2 in the second iteration is equal to 1/6 times 17 minus, but this time I put the x1 and x3's values that I obtained at the end of the first iteration. So x1 is what? x1 is equal to 2.4 and x3 is equal to 2.85, right? So this is what we get. So it outputs the result 1.95 if there is no numerical error, and hopefully I have made no numerical error. 71.43. So this is the value of, this is the actually new value of the second unknown variable in the second iteration. And how about the third variable, right? This is the new value of third unknown variable in the second iteration. Now we will explore what it is, and we plug the same formula here. Okay, we rewrite the same formula. 1/7, 20 minus, this time the values of x1 and x2, and the value of x1 is 2.4 and the value of x2 is 2.83. Well, you may round up, okay, or round down depending on our choice. So what we get here, we got something around 1.138095. So actually now I obtained the new values of each unknown variable at the end of the second iteration. So these would be the actually updated values. So I would update the values of these unknown variables if I proceed to the third iteration. Then what am I going to do here? So the same procedure works here. I will look at the errors, right? So, but this time, what is the error, for instance, for the first unknown variable? Now, in this iteration, I got 1.26. How about in the previous one? So I just look at the successive two iterations. Now, first and second iterations are successive iterations. So in the previous iteration, we got 2.4, right? So guys, there is one thing that you can clearly see, that we are still not able to reach to the desired error tolerance, which is not, this difference is not less than 0.01. And for the other unknown variables, the same thing is true, right? Because 2.83 minus 1.95 is still not less than error tolerance. And again, for the third unknown variable, 2.85 minus 1.13 is not less than error tolerance. And even if I take the maximum again, it is not below the error tolerance. That means we keep iterating, right? So we will go on this way. Okay, so of course I will not continue forever in this manner. At some point we will stop. That's why we have a termination criteria. And in this manner you keep going until when? Well, let's keep going until the 7th iteration. And 7th iteration, actually, when I found the values, if you continue in this manner, in the 7th iteration, I reach to the desired error tolerance. In other words, all the unknown variables satisfy the pre-assumed error tolerance, which I actually found. This is the result of x1. I find something around, I will round off, something around 1.49. And for x2, I use the 2 decimal digits. You're free to use more than that or less than that. It's up to you. It's actually our choice. And for the x2 we got 2.19, and for x3 we got 2.33. And well, actually maybe it would be better to write the results of the 6th iteration as well. Well, this is the results of 6th iteration for you to clearly see that we are actually below the error tolerance as desired. So x1 is around 1.49 and I rounded off, so because that's enough for me. I see the 142, so 2 decimal is enough because I'm less than 0.01, right? So for x2 we get something 2.19, right? And it keeps going, but the rest is not, the remaining digits is not very important after this moment, because this difference, if I take the difference between this and between this, it would be all less than 0.01, which I want, right? To stop the computational process for the Jacobi method. And for the third unknown variable we have something around again 2.32 almost 33, right? So again, and even if I take the maximum of this, so it is less than the desired error tolerance. This is actually what I want. So at some point we need to stop, and this is the reason why we use the termination criteria. We either put an upper bound on the maximum number of iterations, or an error tolerance, or an accuracy rate, right? At some point that would enable us to stop our computational procedure for finding the solution. And this is actually our approximate solution, right? Because what we are trying to find is a 3-tuple that satisfies all the equations simultaneously with the desired error tolerance. This is an iterative algorithm, and it is sufficient for us to have a solution that satisfies our pre-assumed error tolerance or the iteration number. All right, now this is how Jacobi method works, guys, and hopefully we have understood all the steps. Just let's recap just let's recap what I found so far in the last two lectures. So we define what the Jacobi method is and see that it's an iterative procedure. But to ensure the convergence, we need to make sure that we have a square, strictly diagonally dominant matrix. So we just check out to see the coefficient matrix really satisfies these two properties. So for a matrix to be square, it needs to have equal number of rows and columns, and to be strictly diagonally dominant, we check to see if the absolute value of main diagonal entries is strictly greater than the sum of the values in the same row. Well, and of course we again take the absolute values while taking the sum of these values. And if all the main diagonal entries satisfies this property, then it's called a strictly diagonally dominant matrix. And if it's a square strictly diagonally dominant matrix, then we can apply Jacobi method because we will have a unique solution case where we are ensured to have the convergence. And the steps we should take in order to apply this technique is that we rewrite each equation in a way that in each equation actually we isolate one of the unknown variables and then move the other coefficients and the variables to the right hand side of the equality to produce an iteration equation, right? So in other words, an equation is rewritten to be used in the iteration process where we will be able to find the new values for each unknown variable. And then we take an initial guess, and if we are not given an initial guess, we choose that point including all zeros and then put this initial guess to find the results of the very first iteration. And then after finding the results in the first iteration for each unknown variable, in other words, after we explore the new values of each unknown variables, then we compute the errors for each of the unknown variables with respect to the two successive iterations. So we just take the difference and absolute value. Actually, we take the absolute value of the differences of these two values of each unknown variable among the two successive iterations and pick the maximum of them and see whether or not we are below the error tolerance. And you can select an error tolerance as you want. So in this example, I prefer to have an error tolerance of 1/100. So unless we satisfy this error tolerance condition, we keep repeating this process. We compute and find the new values of each unknown variable in each iteration. Until when? Until we are done with the error tolerance, and if all of the errors are less than the desired tolerance rate, then we stop our algorithm, we stop our computational process and produce the output values that we have at that iteration. So in this case, I stop at the 7th iteration, and in the 7th iteration, the values for each unknown variable that I found actually are my solution set, or are the values of my solution set. Okay. And since we have a termination criteria, we are guaranteed to stop sometime in our future iterations. And this is how Jacobi method works, and this is the steps that we should take in order to apply the Jacobi method so as to find a solution to a given system of linear equations. Alright guys, and that's it for this lecture. And in the next lecture, I will show you another iterative method, namely Gauss-Seidel method, which is pretty similar to Jacobi method, but there is a simple difference in the computational process. In other words, when we update the values, there's an important difference actually. And see you in the next lecture, and until then, have fun.